Hello everyone, this video is going to go over the Unit 2 practice exam that covers chapters 5 through 8 in Physics 251. Number 1, write a short description of a real object for which this free body diagram would be reasonable. So we've got a normal force that's perpendicular to this x-axis. We know that there's a kinetic friction force that's present, and we see that the net force is oriented toward the bottom of this incline. So first off, this gravitational force Fg is going to be oriented straight toward the surface of the planet, or if you want to think about it, it's straight toward the center of the planet. That's also valid. Now, we know that we've got an object that's on an incline and the angle theta is shown here, but there are a few clues here that give us some information about the type of event or object that could match up with this free body diagram. So first off, we know that our net force is oriented downhill. So that tells us that the acceleration of this object also has to be oriented downhill. The second big clue is the direction of Fk. This is kinetic friction. So this means that the object is moving in the opposite direction of the kinetic friction vector. So if we call the positive x-axis this direction here, so forward or downhill, then since we know that Fk points in the positive x direction, velocity has got to point in the negative x direction. So this means that this is an object that's currently moving toward the left, or it's moving up the incline, but it's experiencing a frictional force that is causing it to slow down as it moves up. For number 2, we just have a few sample scenarios and we want to sketch free body diagrams for each of them. So for A, a block that speeds up while being pushed across a rough, flat surface. We know that there has to exist some force representing the push, and this is a scenario where it's a sustained push instead of a quick push like we saw in our first problem. We know that the surface is flat, so the normal force and the gravitational force are going to be equal and opposite. But we know that the surface is rough, so there will exist a kinetic friction force because we know that our block is actually moving, it's speeding up. So the net force can't be 0. And if we just arbitrarily choose that the positive x direction is the one that corresponds with the direction of the push, that means that velocity is also going to point in that direction. It means that the net force is going to be in that direction because we know that our block is speeding up. So the force of the push is more than what is necessary just to cancel out Fk. B, what if we have a block that's sliding to a stop on a rough, flat surface? Well, this is kind of similar to the scenario from problem number 1, where we know that our object is in motion. So if we arbitrarily choose to say that the direction of the velocity is toward the right or forward, that means that the kinetic friction vector has to be opposite that. So it's going to point toward the left. However, since the block is on a flat surface, the normal force and the gravitational force will cancel again. So they are equal and opposite. The only unbalanced force comes from Fk, our kinetic friction. So the net force is also going to be negative. C, a block slides up a frictionless 15-degree incline. Well, we know that we have a normal force that will no longer be exactly the same value as the gravitational force. This is because putting the object on an incline means that the normal force is going to split. So in other words, the gravitational force will have one component that's pointing downhill, and that's going to be our opposite or our sine component. There's going to be another component that's perpendicular to the surface, the cosine component, and the normal force is the one that's going to be equal and opposite of the cosine component of Fg. So we have Fg sine theta pointing downhill. And for this one, we know that this is sliding up a frictionless incline, so there's no kinetic friction acting here. So velocity is going to be oriented uphill, but because the unbalanced component of Fg is oriented downhill, that means the net force will also be oriented downhill. D, a block slides up a rough 15-degree incline. Well, D is almost exactly the same as C in that the gravitational force is going to point straight toward the center of the planet. The normal force will have to be perpendicular to the surface. But now instead of Fg sine theta being the only force that is oriented parallel to the surface, we know Fk exists because this is a rough ramp. And if V is oriented uphill, that means Fk has to be oriented downhill. So the net force for free body diagram D would also point downhill. It would just be Fk plus Fg sine theta in terms of magnitude. E, a block is resting on a rough 15-degree incline. So the key word here is resting. We know that the block is not moving, so the type of friction that's acting on the block is static and not kinetic friction. That means that there's zero velocity, and instead of the kinetic friction force pointing downhill, which is what we saw for our previous example, because this is static friction, it's got to point uphill so that it can cancel out Fg sine theta. That's the only way that the net force would remain zero for this block and that the block would remain static. F, a skydiver whose parachute has not yet been deployed. So we're assuming that our skydiver has already jumped out of the plane here. So their downward velocity is going to be something bigger in magnitude than zero. They're not at rest. And as a result, because their vertical speed is something other than zero, drag is going to be present. It's going to be acting opposite the gravitational force. But the parachute essentially exists just to make the skydiver's surface area very, very large so that it interacts in a very, very noticeable way with all the air in the atmosphere and prevents the skydiver from continuing to speed up as they get closer to ground level. So we know drag exists, but we also know that it's not big enough to counteract the gravitational force. So the net force is oriented down. But once the parachute's been deployed, now that drag vector is going to reach its maximum magnitude, which is just whatever the magnitude of the gravitational force is. Now the acceleration goes to zero, but the skydiver is still moving downward. So this is a case of dynamic equilibrium. V is no longer equal to zero, but the acceleration is zero. So there are no unbalanced forces acting on the skydiver. Hi everyone, here's an update to a typo that I didn't discover until I was in the middle of recording this. This is number 2, part H, a crate that slows down as it's being lowered to the floor of a workshop via a rope. So our crate is moving down, but it's moving down while slowing down. That means the acceleration has to be oriented up, which means that the net force has to be oriented up. That tells us that the tension has to have a larger magnitude than the gravitational force does. Number 3, a 1.25 kilogram Peregrine Falcon flies in a straight line that can be described by the following position function. Where t is positive, calculate the net force on this falcon at t is equal to 1.5 seconds. Okay, this is very similar to a practice problem we had in the Unit 1 practice exam, where in that case we were just concerned with determining the falcon's position, velocity, and acceleration at a given time. This is a new function, so we've got to take 2 derivatives of this position function in order to get an acceleration function. So let's start there. If we are beginning with 38 meters plus 2.5 meters per second squared times t squared minus 0.11 meters per second to the 4th power times t to the 4th, then taking one derivative will yield this function here, 5.0 meters per second squared t minus 0.44 meters per second to the 4th power times t cubed. One more derivative of that with respect to time will give us an acceleration function. So this becomes 5.0 meters per second squared minus 1.32 meters per second to the 4th times time squared. Now, the time we're given is 1.5 seconds. We can plug that into our acceleration function to get the acceleration value at 1.5 seconds. And what we end up with is 2.03 meters per second squared. And now, since we know the mass of the Falcon, we can use Newton's second law. If F net is equal to mass times acceleration, and we know the acceleration at t is equal to 1.5 seconds, the net force at t is equal to 1.5 seconds will just be m times a. So 2.5375 newtons, which becomes 2.5 newtons when we apply the appropriate number of sig figs. Number 4, a 14 kilogram block is suspended by 2 cables as shown below. If theta 1 and theta 2 are equal to 21.0 and 37.0 degrees respectively, what are the magnitudes of T1 and T2? So we're beginning with another static equilibrium problem, which means that we know that the net force in both the x and the y directions will add to 0. I have a free body diagram on the right-hand side, where my original forces are shown here in purple. I have T1 that's oriented along the diagonal of cable 1. I have T2 that lines up with cable 2, and then the gravitational force that's just going to point straight down. We're given theta 1 and theta 2 with respect to the horizontal here. So I could just stick with the cosine components for the x direction and the sine components for the y direction. Looking at our free body diagram, it's evident that if we break T1 into an x and a y component, they're going to add back to T1, and then T2x added to T2y is going to give me T2. So I stuck with the cosines here. You could determine what the complementary angle would be for the vertical and then flip your sines and cosines. No matter which of those choices you make, you're going to end up with a net force expression in the x direction that is the negative T1x component added to positive T2x. That's going to get you to 0. So I have negative T1 cos theta 1 plus T2 cos theta 2. In the y direction, there are 3 forces to worry about. I have T1 sine theta 1, which is just the vertical part of T1, added to T2 sine theta 2 because both of those point up. I'm subtracting my only negative force, so gravitational force. All those will get me back to 0. And now at this point, we have a system of equations with 2 unknowns, 2 equations. We can solve this a bunch of different ways. What I've chosen to show here is what you get when you solve one equation for T1 and you plug it into the other one. So from our horizontal net force expression, we can see that T1 is going to be T2 cos theta 2 over cos theta 1. So I can plug that in anywhere I have a T1 in my F net y expression. Now, I moved the gravitational force to the right side because it was my only negative that was on the left side of the equation. And I'm now trying to just factor T2 out. So I have T2 times the product cos theta 2 over cos theta 1 times sine theta 1. I can take that sine theta 1 over cos theta 1 and turn it into a tangent theta 1. And once I have T2 factored out on the left side, I can find that T2 is going to be the gravitational force acting on the box times cos theta 2 times sine theta 1 plus sine theta 2. I think I said times there. This is clearly division, so divided by that quantity down there at the bottom. So I can plug in these values. I will have nothing that has a unit in the the denominator. All my units are going to be in the numerator, and they're exactly what we would expect. Mass units times acceleration units, which will get us to force units. And we find that T2 is 151 newtons when we apply the appropriate number of sig figs. At this point, we could start over and solve the F net x for T2. We could plug that into F net y. We don't need to do that though, because we have a nice kind of simple, concise expression for T1 in terms of T2, which we just calculated and our two angles. So I'll go back to that FNetX expression, plug in our calculated but unrounded T2 value. And what I find is that T1 is 129 newtons. The scan kind of chopped off the capital N here, but that is our final answer for number 4. Number 5, a 15 kilogram block is pushed across a rough surface. The coefficient of kinetic friction is known by a 70 Newton force for 4.0 seconds. We'll assume the block begins at rest. First, we can start with a very basic motion diagram, or even simpler than that, just a pictorial representation of where our block is at t is equal to 0, and then what we know about it at t is equal to 4 seconds. So it begins at rest. We can choose our coordinate system so that the initial position is x is equal to 0 meters. And we know that that push is going to cause this block to move forward. And at some point, or at a time, t is equal to 4.0 seconds, I expect that block to have some positive position and the velocity to be some positive value. Now, everything here on the left-hand side is what we could have accomplished, or what we could have figured out in Unit 1, Chapter 2 in particular. Now, Unit 2 shades in exactly what caused this acceleration to happen. So here's a free body diagram for the block. It is receiving this force that we know has a magnitude of 70 newtons. I've called that F push here. We know that this is a rough surface, so we know there is a kinetic friction force that's going to be opposite the direction of motion. And it's implied here that the direction of motion, or the sign of the velocity, is a positive, so Fk is going to have to be a negative. But the net force is oriented toward the right because F push is larger in magnitude than Fk. I also know that's got to be the case because we know that our acceleration has to be a positive. And once you have the direction of the acceleration, you also have the direction of F net, and vice versa. So for part A, we want to figure out how much kinetic friction is acting on the block. We can go to the vertical net force expression for this, because the only two vertical forces we have to worry about are the normal force and the gravitational force. I know that those are going to add up to 0. So that means that the normal force and the gravitational force have to have the same magnitude. So I can calculate the gravitational force by just taking the block's mass and multiplying it by free fall acceleration. I get 147 newtons for the normal force. But what part A is actually asking us for is the kinetic friction force acting on this block. So namely the magnitude, how much force is what we're looking for. So kinetic friction can be found so long as I know the coefficient of kinetic friction and the normal force, which we just calculated. If I take the product of those two, I will get 45.57 newtons, which is the unrounded value that we're going to plug into our later questions. However, if we're expressing this to 2 sig figs, we would round that to 46 newtons for the magnitude of kinetic friction. For part B, determining the block's net force, I could just take the difference between the two forces that we know are given force F push and the kinetic friction force that we just calculated. And I find that F net is a positive. It is approximately 24 newtons, 24.43 in its unrounded form. But now that I've got that, here's the key. I can use F net to figure out what the acceleration is. And we've already demonstrated that the acceleration is going to be 0 in the y direction and non-zero in the x. F net divided by the mass of the block gives me an acceleration of 1.629 meters per second squared. Now, once I've got that acceleration, I can jump back over to this motion diagram, and this is more or less a Unit 1 question at this point, because I can figure out what the final velocity is for this block. We know it started at rest. We just figured out its acceleration. We know that it's moving for 4.0 seconds. So it would reach a final velocity of 6.5 meters per second. And as far as the distance traveled is concerned, technically you do have some options as to how you could calculate this last bit, because you do have an initial velocity and a final velocity. So we could take that in conjunction with our acceleration. to figure out what the delta x is using our time-independent kinematic equation. But what I chose to do here is just use the first kinematic equation, so the one for position, in terms of the initial velocity, delta t, and our acceleration. And doing that shows that this box moves a little over 13 meters in 4 seconds, 13 meters to the appropriate number of sig figs. Number 6. A 15-kilogram block is released from the top of a ramp made from a rough 2.0 meter board that's inclined 34 degrees above horizontal. The coefficients of static and kinetic friction between the board and block are 0.55 and 0.23 respectively. We can calculate the block's acceleration, its final velocity, and the time that it takes for the block to reach the bottom of the board. All right, I blinked back to the Unit 1 practice exam because this problem that we're solving now is actually based on a scenario that we studied previously. We had a block whose mass we didn't know, but we knew it took 0.85 seconds to get down to the bottom of this 2.0 meter board, but it was frictionless, and we knew that we could take kinematic equations and use it to figure out what the inclination angle is, 34 degrees. So if we're assuming that that is the same board, but now let's say that we are using its rough side, we can make some predictions about the amount of time that it should take for the same block to slide down the rough board, and then how quickly it should be traveling at the bottom. Now coming back to our Unit 2 practice test, we've got our 34-degree angle. We now know that this is a 15-kilogram block, and we've got our coefficients of friction for the block and the board. Now, first off, if I make a free body diagram, I have the gravitational force that points straight down or straight toward the center of the planet. I have the normal force that's perpendicular to the surface. So that normal force's magnitude is not going to be the same as the magnitude of the entire gravitational force, but just this one component, so the piece that's perpendicular to the surface as well. And that's going to be Fg cosine theta. The sine component is going to point downhill. So this is essentially what we named F incline when we were working in our Newton's second law lab. If our block is moving downhill, then kinetic friction is going to point the opposite direction. So it's going to be oriented uphill. And we know that the block does actually slide, so we know Fk is not large enough to counteract Fg sine theta. So the net force is going to be oriented toward the bottom of the hill. I'm calling that forward in the positive x direction. So if I look at the net force in both directions, I have Roman numeral number 2 here, which is just my definition of the normal force in terms of cosine theta and mg, which is the gravitational force. I can plug that normal force into Roman numeral 1, where I'm trying to calculate the kinetic friction acting on this block. If I come over here to the right side, I've got essentially equations 1 and 2 combined. I can solve this for the acceleration. And there's a huge clue as to why I can do this without actually using the mass of the block. And it's essentially something that takes us back to our Unit 1 logic. I didn't need to know anything about that block's mass. I just was trying to model how it was moving down the ramp. Now we're looking at why it's doing what it does. But I have an m in all 3 terms. I can cancel it out. And the acceleration is going to be free fall times this quantity sine theta minus mu k cos theta. If I plug in those values, we get 3.6 meters per second squared that we can compare to the acceleration that we calculated for the earlier version of this problem. That was just g times sine theta. So 9.80 times sine 34. Coming back to our Unit 2 version of the problem, the maximum speed that the block reaches at the bottom of the board should be less because now this board is rough as opposed to being frictionless. So we have one real option here because we don't know anything about the amount of time that it takes for this block to get to the bottom of the board. So we can use the time-independent kinematic equation. V final x is our unknown. V initial x we know is 0. And ax is something that we just calculated. So if we use that with the length of the ramp which we were given, we do indeed get a final velocity that's smaller than the previous one. The previous one being 4.7 meters per second. Now for part C, we do actually want to know how much time it takes for this block to slide down the ramp. There are two options. You could either use the kinematic equation for position because we know the acceleration, we know delta x, and we know v initial. However, a more concise way to get to the same information is to use our second kinematic equation, so the one for velocity. V final is v initial plus the acceleration times delta t. We know the v initial is 0. We just found the final velocity in our previous question, and we calculated the acceleration further up. So that time is 1.1 second. So it's logical that it would take this block slightly more time to get to the bottom of the same ramp if now the ramp has friction compared to a perfectly frictionless one that we saw for before. Now, part D doesn't really line up specifically with anything from part 1, but it's asking us to figure out what the largest angle the board can reach is before the block is guaranteed to slide. So when we calculated in part 1, or excuse me, unit 1's practice exam, that the angle that would allow this block to travel 2.0 meters in this time, 0.85 seconds, that angle was 34 degrees. So setting the block on the ramp that was inclined 34 degrees meant that the block was going to slide because FG sine theta is oriented downhill. Part D is asking us to consider what the static friction value would max out at if I had now the ability to raise or to adjust the angle of this ramp. So my writing is a little bit small here, but I introduced a theta nu so that this is theta nu measured with respect to the horizontal. The cosine component of the gravitational force is Fg cosine theta nu. Fg sine theta nu is pointing downhill. The normal force is the same as we drew it before, and now the type of friction that is acting on the block is static instead of kinetic. So our goal is for F net to be 0 and stay 0. I can start with net force expressions for the x direction, and I just used our earlier conclusion that the normal force was going to be mg cosine theta, and I just added cosine theta nu here, so we know it's not the same angle as before. But I can plug that into our static friction expression, which is just mu s times the normal force. And some interesting things happened here. I have two forces that I want to add up to 0. So I'm going to have an mg on each side of this equation. Mass and free fall acceleration cancel out here, so that I find sine theta nu is equal to mu s times cosine theta nu. If I divide both sides by cosine, I have tangent theta nu is equal to mu s. So I can just take an inverse tangent. And we end up with 28.811 degrees, so that's 29 degrees to 2 sig figs. And if we compare this to our original scenario, if I want to imagine the board starting flat and then I slowly incline it, I know that once I get to 29 degrees and I pass it by, the block is going to start to slide. And that makes sense with where we started off with. We were already at an angle that was above the largest angle that the board could have while allowing the block to sit still. Number 7 is a Newton's third law problem. 3 identical blocks, each of mass 0.250 kilograms, are connected by massless strings as shown below. So, in other words, we are allowed to think about the strings as simply being there to deliver force from one point to the next. We're assuming that the strings start off taut at t is equal to 0 seconds. Assume the blocks lie on a frictionless surface, and they're observed to have an acceleration of 1.50 meters per second squared when acted upon by a force F. So you can imagine maybe attaching a string to block C and then dragging all three of them, or you can imagine this force F is just your hand grabbing the block and dragging them all. Now, there are a couple of things that I have noted here. I'm not saying anything about the vertical forces acting on these blocks because I know they're going to cancel. This is a flat surface. It's a frictionless surface. So the vertical forces balance out. I know that the horizontal forces don't balance out because there's an acceleration in the horizontal direction. So because that acceleration has to be the same for all three blocks, there's no point in holding on to the subscripts on this acceleration. I'm just going to call them A. So I have block A that's at the end of the chain. It receives a force from the string that connects it to block B. So we can call that tension of B on A. There is another corresponding half of its third law pair, TA on B, that is acting on block B as a result of the string connecting it to block A. There exists a TC on B that's also acting on block B. And then, of course, that has to have its own third law pair on the other side, TB on C, where block C is the one that you're actually interacting with directly. So it's also receiving this force F oriented toward the right. Now, because we know the masses of all three blocks, there's more than one way we can approach this, but the one that I chose to show here involves starting at the end of the chain and then using what I know about the unbalanced forces acting on block A to say something conclusive about the net force on block A. So here I'm just going to simplify this notation a little bit. TB-A just means B on A. We're not subtracting anything here. But because that's the only unbalanced force on block A, that has to be equal to F net. No matter what, F net's going to be equal to the mass of block A times our acceleration. So if I put those together, I can solve for TB on A, which is just mass times acceleration, the two things we started off knowing. I find that TB on A has magnitude 0.375 newtons. And technically, we are looking for TA on B as one of our tensions. So TA on B is going to have the same magnitude, but just negative. And TA on B does point toward the left, so that makes sense that that's a negative in our coordinate system. But once I know the magnitude of both TB on A and TA on B, I can use that as I move down the chain. So I'm going to block B now. I know block B is receiving two horizontal forces, but they don't cancel out because block B does still accelerate along with the rest of the blocks in this chain. I have two forces, so TC on B minus TA on B, because TC on B is forward, TA on B is backward. No matter what, F net's got to be equal to the mass of block B times A. So I can rearrange this expression. I'm solving for the one force I don't know already here, which is TC on B. That's just going to be the magnitude TA on B plus the net force on block B. And I want to call attention to the fact that this statement down here is just dealing with magnitudes. We do know that the direction of TA on B is going to be a negative from our previous conclusion, but I don't need to count that direction or that orientation a second time. I already made a decision about it right here. So TC on B is going to be 0.750 newtons. We're asked to comment on TB on C, so TB on C is going to be the same magnitude, but it points toward the left, so negative 0.750 newtons. And then finally, we get to the last block in the chain, block C. It's receiving this positive force F, this negative force TB on C. I know how large TB on C is. I don't initially know the applied force that it takes in order to accelerate all these blocks to 1.50 meters per second squared, but I can use the same approach that we used for block B. I can set these net force expressions equal to one another and solve for my one unknown force, and we end up getting 1.125 newtons. We have 3 sig figs on this problem, so we can call that 1.13 newtons. Number 8, this is our traditional Atwood machine, so the one that has 2 blocks that are only free to move in the vertical direction. There's no horizontal surface that either block is sitting on. So that means that I start off knowing immediately that the net force acting on each block is only going to exist in the y direction. I have a 15 kilogram block and a 13 kilogram block. And we're assuming that our pulley is massless and frictionless, the string is massless. Those are just devices that transfer force from one point to the next. My starting point should always be drawing a free body diagram. So I know that in this case here, M1 is the larger of the 2 masses. So the gravitational force that acts on block 1 is going to be larger than the upward tension force that acts on block 1. In other words, I know that block 1 is going to drop toward the floor, so F net 1 should be a negative. I can say the opposite for block 2. Block 2 has a gravitational force that's smaller in magnitude than block 1, but it's going to be small enough that this tension T2 will be able to accelerate block 2 toward the ceiling. Now, here I have T1 and T2 identified separately. For this idealized Atwood machine, we're going to come to the conclusion that T1 and T2 are the same. We'll be able to investigate a slightly more realistic version of this when we get through Unit 3. But at this point, I do drop the subscripts off, so T1, T2 just show up as T in these equations. I need to say something about the acceleration because I know that the acceleration of block 1 can't be different than the acceleration of block 2, but their signs are going to have to disagree because it's not possible for both blocks to accelerate up or both blocks to accelerate down. It's got to be one of each. So if block 1 is the one that's going to drop toward the floor, I'm going to say A1 is negative, A2 has the same magnitude but is positive. I'm just going to call these A. And up here at the top, it's quite tempting to try to match these net forces together because it's evident that something about how block 1 is experiencing this scenario and how block 2 does, something about that has to be the same, but it's not the net force. So F net 1 and F net 2 are not going to be the same, but I can use my free body diagrams to write out net force statements for each block. And initially, T minus the gravitational force, that's going to show up 2 different times, where the only difference is that I'm going to switch out the masses because block 1 and 2 don't have the same mass. Now, the other part of this, F net is going to be mass times acceleration. I know block 1 is going to experience a negative net force, block 2 is going to experience a positive. And at this point here, you have some options as to how you can solve this system. 2 equations, 2 unknowns, just like a couple of our other examples. So what I chose to do here was just to take each net force expression and then write it out 2 ways. One way that solves for tension in terms of block 1's mass and accelerations, and then I did the same thing but for the acceleration in terms of block 1's mass, free fall acceleration, and tension. If I do the same thing for block 2, I'll have 2 equations for the tension that I could set equal to one another, 2 equations for the acceleration that I could set equal. Again, this is not the only way, but just the way that I chose to represent here. So on the left, if I take the 2 equations that I have for the acceleration, if I set them equal to one another, I can cross multiply so that I can isolate T by itself. And I have a positive M1, M2G on one side, a negative M1, M2G on the other. So these don't cancel, they add together. And I find that the tension is going to be 2 times the product of the masses times free fall acceleration divided by the sum of the masses. And when I plug those values in, I get a tension of 137 newtons. So this tension has to be more than enough to support one block, but not enough to support the other block. Now, if you chose to eliminate tension first, then you would have followed the same procedure that I have here at the bottom right. I set those two T statements equal to one another, and then I worked on isolating A. And the acceleration that I have here is free fall acceleration times the difference between the masses, all divided by the sum of the masses. And because these two masses are pretty close in terms of their value, they're only 2 kilograms off, the acceleration value that we get here should be closer to 0 than it is to free fall, but it would have to have some positive magnitude. To say that another way, if I had two very, very lopsided masses, then that acceleration value that we would expect to find should be closer to 9.8. But if you get 9.8 on the nose when you're solving a problem like this, what you've done is you've made a coordinate system issue. Either you have too many negative signs or you have too few negative signs. Otherwise, the rope would seem to imply that it has no ability to prevent both blocks from experiencing free fall, and that's not logical. Okay, so we have the acceleration of 0.700 meters per second squared. Of course, once you get either T or A, you could just double back to your original equations and then plug them in to get the other quantity. Now, number 9 is a more complicated Atwood machine. This is a modified Atwood because it's not just two blocks moving vertically. Here we've got one block that's on a flat surface, one that's on an incline whose value we know. We know our two blocks have the same mass, 40 kilograms in this case, but they're on rough surfaces. And since it's the same surface and two identical blocks, this coefficient of kinetic friction that we're given applies to both block A and block B. Again, we're assuming that this apparatus has a bunch of massless strings, and it's not commented on here, but you should assume that you're dealing with an idealized pulley unless you're told something to the contrary. So the pulley produces no friction, the pulley has no mass, thus it costs no energy in order to start turning. But just as we had before, we can begin by drawing two free body diagrams, one for block A, one for block B. And up here at the top, I'm just reminding us that since we've got identical blocks, MA and MB are eventually just going to be called M. TA and TB are eventually just going to be called T. And then acceleration A and acceleration B, I'm just going to call that acceleration. So the blocks are identical, but one's on a flat surface and one's on an incline. So their normal forces are not going to be identical. Block A is going to have a normal force that's exactly as big as the gravitational force, just in the opposite direction. I know that block B, or the rope connected to block B, is going to cause block A to experience a tension that's oriented to the right, but we're given the direction of FK. So what this implies is that we know that block B is going to slide down the incline and it's going to drag block A to the right. So the net force on block A is going to be oriented to the right. If I look at block B, it's a little bit more complicated, but still understandable because we know block B's gravitational force points straight down. The normal force on block B is just going to be perpendicular to the surface so that it cancels out the cosine component of FGB. I know the tension acting on block B is going to be pointing uphill, the same direction as the kinetic friction acting on block B. So all that means is that FGB sine theta is large enough that TB and FKB can't cancel it out. There's still some net force left over that's oriented downhill. So I begin with net force expressions for each block. For block A, there's not really anything really notable happening in the y direction, but I can confirm that the normal force is just going to be the mass of block A times free fall acceleration. I can plug that in to F net x for block A. And I get this expression for the acceleration. So TA minus mu k times ma times free fall acceleration divided by ma. That's the acceleration of block A. That also has to be the acceleration of block B because these are interacting objects. I can define block B's acceleration by starting with block B's net force expressions. So in the x direction along the surface of the ramp, I've got the gravitational force times sine theta. So mb times g sine theta. TB points uphill, so I'm going to subtract that off. FKB also points uphill, so I subtract that as well. But since block B is accelerating forward, which is in the positive x direction for the choice I made here, then the net force on block B is also going to be a positive. And my net force expression in the y direction is what tells me exactly how big the normal force is. So that normal force NB is something that I can plug into this kinetic friction force expression. So I do that there. I solve this for A. It's the mass of block B times g sine theta minus mu k times mb cosine theta. And I think I lost track of a g in this step here, so I apologize for that. Minus tb, all that over mb. That's going to be the acceleration. So I can plug both of those in. I can set them equal to one another. And at this point here, I did just completely let go of the subscripts. So tension is just T, masses are just M's. And what I end up with is 2T is equal to mu k mg plus mg sine theta minus mu k mg cosine theta. So again, this is where that g that I lost up here should go in that middle term. It shows up again down there. I apologize for that. So I can solve for t. I get 40 kilograms times free fall acceleration divided by 2, all multiplied by the statement that's in the parentheses. And there's nothing that has units inside there. I'm just looking at mu k sine theta and then mu k cos theta. I find that the tension rounds to 102 newtons when we apply sig figs. And then here at the bottom, I took that tension, I plugged it back into Roman numeral 1 to solve for the acceleration, because that's a nice, concise, pre-existing expression for that. I have my unrounded tension minus mu k mg, and the scan chopped this off here, I'm sorry, but this divides out mass, so that's 40 kilograms in the denominator here. I end up with an acceleration of 1.08 meters per second squared. Number 10, a regulation baseball has a mass of 145 grams, a radius of 7.5 centimeters, and a drag coefficient of 0.33. So something that is notably less than the smooth sphere that we saw in our notes that was about 0.50. Our questions: how much drag does this baseball experience when it's thrown at 45 meters per second? What terminal speed would it reach if it were dropped from a great height? So for the first part of this, if we're just trying to approximate the drag that's acting on this baseball, we need to know the coefficient which was given to us. We need to be able to calculate the cross-sectional area, where here I believe I did write 0.74 meters, but used 0.75 or 0.75 meters in the calculation. I need to know the density of the air that's moving through. This is a constant, not something that you would be expected to have committed to memory. So this is on our formula sheet. It's 1.28 kilograms per cubic meter. And then the speed we're given is 45 meters per second. So if I plug in those values, what I will get is a force, because everything except for 1 kilogram, 1 meter, and then 2 or squared seconds, everything but that cancels out. We're left with 7.6 newtons of drag when the ball is moving at this speed here. But the terminal speed that the ball would be capable of experiencing if it were just relying on Earth to accelerate it, that's going to be a different value. So something that is less than the like initial velocity that a pitcher could deliver to this baseball by exerting a very large force on it. Earth is only going to be capable of exerting a force that's this big, so mass times free fall acceleration. And terminal speed is reached when those two forces perfectly cancel. So the ball is still moving, it's just no longer capable of accelerating anymore. And we've got in the y direction, drag minus the gravitational force is equal to 0. I can plug in our expression for drag. I can plug in the expression for the gravitational force on the other side, and I can solve for v, where specifically this is v terminal, whereas this v that we were working with earlier is not the result of Earth accelerating the baseball and then air resistance reaching its maximum value. So if I solve for that terminal speed, I would find that that baseball of like these dimensions, this drag coefficient, etc., this would be capable of reaching a speed of 20 meters per second if it were only relying on Earth to accelerate it. Of course, if you're relying on the pitcher to exert a large force on it, it is perfectly capable of surpassing 20 meters per second. Number 11, a highway is designed such that a 1,500 kilogram SUV can move around a curve of radius 210 meters at 25 meters per second without having to depend on static friction. So this requires a banking angle. That means that the road surface is not going to be perfectly flat. Instead, it's going to be inclined such that the normal force actually ends up being bigger than it would be if this car was just traveling around on a flat surface. So there are three things that we can investigate here. We want to figure out what banking angle allows this car to travel around this curve without needing to depend on static friction. So in other words, we're looking for this critical speed V0. And we can begin by writing net force expressions for each direction. So in the radial direction, assuming that our car that's not shown here is driving right into the plane of the screen, so that's our tangential axis is going into the screen. That means that the radial axis is going to point toward the center of our circle, which would be to the left. And we can find that this net radial force is going to depend on the r component of the normal force, so n sine theta, because if I know the banking angle, I also know that the angle between the normal and the z-axis will be theta as well. That has to be equal to mv tangential squared over r, where that's scanned kind of badly here. But if I solve this expression for the normal, I get mv0 squared over r sine theta. And I changed the subscript here because we're looking for this special case where the tangential speed is equal to v0. Now, if I look at the z-axis, I can see that there's a cosine component of the normal that's unaccounted for, and that's going to balance out the gravitational force, which is just m times g. So n cosine theta minus mg, that's going to add up to 0 because the car doesn't accelerate up along the z-axis, nor does it accelerate down in the z direction. And here we end up with this normal force that is not just mg times cosine theta, but mg divided by cosine theta. And again, that's because the entire reasoning behind banking this road surface is so that it makes the normal force acting on this car bigger than what it would be if it was just on a flat surface. So I've got two expressions for n. I can set these equal to one another, and I find that the mass of the SUV cancels out here. So this banking angle wouldn't be appropriate only for cars that have that specific mass, but for any car that's traveling at the given speed and traveling around a curve that has this given radius. I can cross multiply here and again recognize that the v tangential that I'm looking for is specifically this critical speed, v0. And cross multiplication shows me that v0 is going to be equal to this should be the square root of gr over tan theta. Excuse me, gr times tan theta. In this question, we're trying to solve for theta, so I can just take the inverse tangent of this ratio VO squared over G times R. The initial speed or the critical speed that we're working with here is 25 meters per second, so I can plug that in the numerator, and I've got free fall acceleration times the radius of the curve here in the denominator. So meters squared over second squared in the numerator and meters squared over second squared in the denominator. If I take the inverse tangent, I get an angle that rounds to 17 degrees. But the point here is that any car should be capable of making it around this curve, so long as it doesn't have incredibly bald tires. It shouldn't just equate to one safe speed and then every other speed being unsafe. The only difference here is that for speeds that are either above or below this critical speed, some static friction is going to be required. So what if we choose a speed that's below? If it's 20 meters per second instead of the 25 meters per second that we're working with, here's what our free body diagram is going to look like now. There's still a net radial force that points toward the middle of the circle. There's still a normal force that's perpendicular to the road surface. Still a gravitational force that points straight down, independent of the road surface. But now static friction is going to prevent the car from drifting downhill, because the car is actually moving at a speed that's below this critical speed. So there's a component, or really just the presence of this static friction force, that means that there's going to be a sine component and a cosine component that I have to put into these net force expressions. So F net radial, in the radial direction, it's going to be the sine component of the normal force minus the cosine component of Fs. Because if this angle is equal to theta, this angle is also equal to theta. So the radial part is going to be the cosine, and it's negative because it's pointing the opposite direction of the normal. But no matter what, as long as that car is moving, then there exists a radial force that's mv squared over r. I can solve this for n so that I can eliminate it, and I can start over with my net force expression in the z direction. So I've got the cosine component of the normal force that points up. That points in the same direction as the sine component of Fs. So I'm adding those together, subtracting the gravitational force out, and I know that the car doesn't accelerate into the z-axis, the positive z-axis, or into the negative z-axis. So those three forces add to 0 in that direction. And I can solve that statement for the normal force as well, and I can set these equal to one another to eliminate the normal. I can do some cross multiplying, and I end up with this step here. So mv tangential squared times cos theta over r is being added to Fs cos square theta. That's equal to mg sine theta minus Fs sine squared theta. So if I factor out, or if I isolate the terms that involve Fs, I'm going to end up with Fs times cosine squared theta plus sine squared theta. That is just 1. That's why it's canceled out here. I didn't write it out completely, but you can demonstrate that you will just end up with a 1 there. And Fs is going to be mg sine theta minus mv squared cos theta divided by r. And when we plug in our values for the mass of the car and the angle that the road surface makes, we find that the static friction that is required in order to allow a car to successfully make it around this curve at 20 meters per second instead of 25 is 1,500 newtons. And again, that static friction is going to prevent the car from drifting downhill. The opposite should be true if we have a car that's moving above that critical speed. So the critical speed was 25 meters per second. What if we choose 35 meters per second for our larger tangential speed? This is a tiny free body diagram, I apologize, but the only thing that is different now is that Fs is pointing downhill. So when your car is moving above that critical speed, static friction is going to prevent you from drifting uphill instead of drifting downhill. But my approach is exactly the same. I can write a net force expression for the r direction. It's going to be n sine theta plus the cosine piece of Fs. That's got to be equal to mass times v tangential squared over r, because as long as that car is moving with some bigger tangential speed than 0, there exists a net radial force. If I look at the z-axis, I've got z cos theta minus now the sine component of Fs minus mg. That adds to 0. So I have two statements for the normal that I can set equal to one another. And once again, when I cross multiply, I run into exactly the same situation as before, where I'll have an Fs times sine squared theta plus cosine squared theta. I can just cancel that to a 1. And again, I'm sorry, the scan kind of chopped off the bottom of this here, but this is dividing by 210 meters, which is the radius of the curve we're concerned with. This is mv squared times cosine theta over r minus mg sine theta. And again, this is hacked off a little bit here, but the unrounded value that you get is 4,100.79 newtons of friction. So that would go to 4,100 newtons when we apply seg figs. Number 12, Earth's mass is 5.98 times 10 to the 24 kilograms. Earth's radius is 6,371 kilometers. You're asked to coordinate the launch of a satellite that will orbit once every 18 hours. What should the altitude of the satellite be? Okay, so one thing that's very tempting to do in this situation is to take the expression for free fall acceleration, which is shown here. Small g is the gravitational constant times the mass of Earth divided by r squared. It's super tempting to just plug in a 9.8 there. But remember, that is only really something that's allowable if you are dealing with something that is physically on Earth's surface or relatively close to Earth's surface. And for a satellite that needs 18 hours to orbit, we're too far away from Earth's surface to treat lowercase g as if it is still 9.80 meters per second squared. Instead, we've got to recognize that this altitude h is measured with respect to Earth's surface. RE is the radius of Earth, so that's from the surface down to Earth's center. If I add those two together, I can call that lowercase r. So that's what shows up in the denominator right here. I need to calculate, or at least algebraically represent, the value of lowercase g at this altitude h. Now, we're given a period in hours. We can turn that into seconds. I don't know why I wrote kilometers there, but 64,800 seconds is the period for this. And this is just our definition for what small r is, Earth's radius plus the altitude. I can take this expression for an orbital period and rearrange it so that I'm solving for g. This is in terms of this 2 pi radian, r, which is, I should say small r, which is capital RE plus h, and then the period squared in seconds. If I set those equal to one another, I get an expression that has a bunch of constants, so the capital G, Earth's mass, and then of course Earth's radius and our altitude, which are unknown. I can set these equal to one another and solve for r, which is legitimately going to require a cube root here, because when I cross multiply, I have r squared that's going to multiply by this r that's already in the numerator. So this is the cube root of the gravitational constant times Earth's mass times the period squared in seconds, all divided by 4 pi squared. When you carry that out, you get a large value. So this works out to 34,876,998.1 meters. We're not looking for small r, we're looking for the altitude. So we have to subtract out Earth's radius to get that. So h is small r minus Earth's radius. We're given Earth's radius in kilometers, so I need to turn that into meters in order for these units to work. My other option would be to turn small r into kilometers. No matter what, though, you will get something that rounds to either 29,000 kilometers or 2.9 times 10 to the positive 7 meters. So in this case here, we had an orbital period. We wanted to figure out the altitude that would allow that period to be possible. What if we work in the opposite direction? Let's say we have an altitude, we want to calculate what the period should be. So we've got 12,000 kilometers for our altitude. We're using exactly the same expressions as we used before, but in a different order primarily. And what I chose to do here was to just calculate lowercase g outright so that we could see just how much smaller it was compared to the value that we use whenever we're working on or very near Earth's surface. So again, I plugged in the altitude that we were given with the radius of Earth. I put both of those into meters so that the units canceled out the way that I need them to. And at 12,000 kilometers, free fall acceleration is only about 1.2 meters per second squared. I can take that small g and then plug it in to this orbital period equation. So 2 pi times the square root of the ratio r over g. I have the radius and the altitude in the appropriate units. If I divide that into, or divide that by an acceleration, then underneath the radical, I'm just going to be left with something that has units of seconds squared, so that when I take a square root, this is just going to give me a time in seconds. So that time in seconds is 24,772.26 seconds. But since 1 hour is 60 minutes and 60 seconds, 1 hour or 60 minutes with 60 seconds per minute, a single hour is 3,600 seconds long. So that's how we get to 6.881 hours. We can round that to 6.9 hours using the appropriate number of sig figs. Number 13, a 2.0 kilogram mass is connected to a 0.85 meter string and swung in a vertical loop. What is the critical speed that will allow the mass to complete the circle? What's the tension in the string at the top of the loop if the mass is swung at 5.0 meters per second? And then what is it at the bottom of the loop if it's swung at 5.0 meters per second? So for vertical loops, now we need to think about whether our r-axis is going to point away from Earth's surface or toward Earth's surface. And for part A, if we're calculating the critical speed, what we're trying to find is the absolute minimum speed that's required in order for this mass to successfully make it around the loop instead of allowing the string to go slack and the mass to just fall downward as if it were in free fall. So the tension still exists here. The string is still connected to the mass, but the critical speed happens when the tension drops to 0. If I look at my net force expressions here, the radial direction is the only one that's actually meaningful here for us. So I have this tension force that I drew just so that we could get a handle on the direction, and the gravitational force that would point toward Earth's surface. So we're imagining that this curve here just shows the top half of this vertical loop. They both point toward the center of the circle, so we're going to treat both of those as positive forces. And so long as the mass is moving, if V tangential is anything other than 0, then F net radial is going to be a non-zero value. I can solve this for V tangential, specifically for the condition where tension goes to 0. And what I find is that this critical speed is mass independent. It depends on the place where this is happening, so free fall acceleration, and the length of the string, not the mass of the object. So I solve for V critical. I'm going to end up with 2.886 meters per second, so that's 2.9 meters per second to 2 sig fig. What it tells me is that if I choose any tangential speed that's bigger than 2.9 meters per second, the mass is certainly going to make it around the loop, but the tension in the string is not going to be 0. It's going to be some positive magnitude. So if I know that I'm swinging at 5.0 meters per second, then really nothing about my net force expressions is going to be different compared to what we had to consider for part A. Only now I know that this tension is not 0. It's got to have some positive value or some positive magnitude. So instead of just plugging in a 0 like we did before, I can set these equal and solve for t. And what I've got is this mv tangential squared over r term, which is the radial force, and then m times g, which is the gravitational force. And if I'm solving for tension, then the tension at the high point in that loop is going to be 39 newtons when you apply the appropriate number of sig figs. So this is kind of equivalent to the feeling of airtime or weightlessness that you might feel if you are on a coaster or like an amusement park ride that brings you around a curve like this. However, if you're on the other surface of the curve, if you're at the bottom of the loop, then what you tend to feel is the exact opposite. You feel heavier than you would if you were either sitting still or if the car were moving along a flat surface. What's different? What's different here is that now the tension and the gravitational force don't point the same direction. The gravitational force is pointing away from the center of the circle. The tension is pointing toward the center of the circle. So we're going to treat the tension as the positive and the gravitational force as the negative. I can put these two equations together for the net radial force. And this time when I solve for tension, I'm not looking at the difference between the radial force and the gravitational, instead the sum of those two. So if I plug in the same mass, the same speed at the bottom of the loop, the same string length, I'm going to end up with a tension of 78 newtons as opposed to only about 39 newtons. And then finally here we have a conical pendulum. So this is what you get when you attach something to a string, you anchor the string, and instead of just swinging the mass back and forth the way that a clock's pendulum might behave, you set this up so that the mass is tracing out a circle in a plane that's parallel to the floor. So let's imagine that we have just a snapshot of this string and this mass while it is while it's moving with some tangential speed that we can calculate. We know the string has a length of 1.20 meters. The mass is 750 grams, so we can turn that into kilograms. And we know that this string is making a 21-degree angle with the vertical. So finding the tension in the string is going to be more than just calculating m times g, because the string tension has got to be greater if this mass is moving in a circle in this fashion compared to what we would calculate if the mass were stationary and the string were just oriented straight up. In that case, the tension would just be m times g. But because it's behaving in the way that it is, it's traveling in a circle, I can look at the net force in the z direction and realize that this gravitational force, m times g, is now just making up one component of tension. It's not the whole story here. But I know that this angle that we're given is 21 degrees with respect to the vertical, so t cosine 21 is going to give me this z-axis component. I subtract off the gravitational force. That has to equal 0 because spinning an object like this wouldn't make the mass accelerate toward the ceiling. It also wouldn't make it accelerate toward the floor. So I know those balance. I can solve for tension, and the tension value that I get is greater than just the gravitational force acting on the mass. This is more like 7.9 newtons as opposed to 7.4 newtons. But once I have that tension, I know that the radial component of this, that has to be the source of the radial force. The radial force isn't like an exotic new type of force that comes from a different place. It is always one of the familiar forces. So it can be a normal, it can be friction, it can be tension, which is the case here. So if we found that the hypotenuse of this little right triangle is 7.87 newtons, if I want to calculate the horizontal leg, that would give me the magnitude of the radial force. So t sine 21 gives me about 2.8 newtons. And if I want to find the tangential speed acting on the mass, I can take that 2.8 newtons and set it equal to mv squared over r, where the mass is given. Here's where we're going to have to recognize that if our string is 1.20 meters long and the angle that the string makes with the vertical is 21 degrees, then 1.20 sine 21, that has to be the radius of the circle that this mass is tracing out. So that's where 1.20 meters times sine 21 comes from in the denominator. I end up with a tangential speed that rounds to 1.3 meters per second. I made an error with the units here, 1.3 newtons. That's a typo that I believe is fixed on the original, the blank version of the Unit 2 practice exam.